Hello everyone, hope you guys are doing well. In this series, we're going to talk about the covalent bonds and then we're going to continue off with the intermolecular forces and finish off with metallic bonding. So this is the second part of covalent bond. In here we start with the revision of covalent bonding. We know that covalent bonding happens through sharing of electrons, and in ionic we lose or gain electrons. So when you share electrons, you still have an electrostatic force, whether it's a nonpolar or a polar bond. And I will show you how. For example, we know that the nucleus is a positively charged while the electrons are negatively charged. When you have a sharing of electrons in the middle, this nucleus is gonna attract to itself the electron, while this nucleus will attract the electrons and the electrons will be attracted this way. So we will have a bond. They will make a bond with each other, so it will be nonpolar. An example was hydrogen was given to us. We know that the electronegativity difference for hydrogen is going to be 0. That's why it is nonpolar. And for the polar ones, for example, we have here hydrogen fluoride. We know that the electronegativity difference gotta be more than 0.5 for that, but less than 1.7 or 1.8. So if you have this type of covalent bonding, you have electrons shared again in between them, but we know that because fluorine and we have here hydrogen, because fluorine is more electronegative, it will pull electrons closer to himself, making it partially negative and himself partially negative and hydrogen partially positive. That's why we have a negative and positive, and they will attract each other. And this is the nonpolar one. So we have examples of nitrogen, hydrogen, chlorine molecules. We know that the methane electronegativity difference is less than 0.5, and that's why it is nonpolar 2. But for this guy, we know that the carbon electronegativity difference with the oxygen is going to be 0.89, which makes it nonpolar. But let me tell you something, that this is a nonpolar molecule too, and I will explain you why. Before this, I want you to read this line. It says all molecules with nonpolar bonds are nonpolar. So if you have nonpolar, then it's nonpolar for sure. But molecules with polar bonds can be both polar and nonpolar. And let me explain you why. For example, we know that carbon and oxygen we have in here, and then we, from the P table, we can find that the carbon electronegativity value is 2.55 and oxygen is 3.44. So electronegativity difference is 0.89, which is more than 0.5, and we are expecting it to be a polar molecule. But we know that this bond is polar because oxygen will draw electrons closer to himself, which is more electronegative, and this oxygen will draw electrons to himself. But this guy is linear, you see, both sides. And we know from physics that two vectors, when they pull each other with the same way, with the same amount, they will add up to 0. They're going to add up to 0. So in the end, it would be non-polar molecule. Okay? Molecule. It is a polar bond. It is, you see, we say that over here. We have a polar bond, but it can be non-polar, and in this case, CO2 is non-polar. That's why we need to know the molecular geometry. If we know their molecular geometry, we would know if the polar bonds make the polar or non-polar compound. Okay? So now we're going to talk about the coordinative covalent bond. we're going to come back to this topic, don't worry about it. So, coordinate covalent bond. We know that before, non-polar bonds or polar bonds happen by sharing one electron from each guy, right? So hydrogen and another hydrogen, they would bring each one electron and will make a bond. And same thing with hydrogen fluoride. Each brings one electron, so fluoride is like this because we got 7, and they make a bond like this. They shared the bond, okay? So hydrogen is shown, one brings each. This is called covalent bonds, right? But now we have another case where we have 2 electrons coming from one guy and then the other electron. There is no electron in the other element, okay? And we said that we need 2 electrons to make a bond, right? So this guy will donate his electron into the middle. They will have 2 electrons and they will make a bond. And this bond was called coordinate covalent bond, okay? So it is shown in here. So pair of valence electrons available for bonding. You see this guy, he donates 2 of his electrons. Now we have octet completed. Look at here, I got 1, 2, 3, 4, 5, 6, 7, 8. And same thing for this guy. This is gonna be 1, 2, 3, 4, 5, 6, 7, and 8. So octet rule completed for both. And this happened through coordinate bonding. Okay, so I'm gonna show you a few of the compounds in here on how to draw their coordinated bond and how we start from the scratch. So I got hydronium ion, ammonium ion, and carbon monoxide. Okay, so let's do the Lewis dot diagram first, but you need to understand this guy itself, the hydronium ion, is a combination of water with a hydrogen ion. The way this happens is that when you have a water in acidic environment, we make hydronium ion. And this ammonium ion, same thing happens from ammonia, NH3. If you add it inside the acidic environment, you get ammonium ion. Okay, so this is again the acidic environment, and CO is another case. So let's start with the water. We're gonna do Lewis dot cross diagram of water. So we got oxygen where the oxygen electronic configuration is 1s2, 2s2, and 2p4. So we got 2 electrons in the first shell and 6 electrons in the last shell. So we're gonna draw oxygen with 6 electrons, and hydrogen is 1 electron, so it'll be 1s1. So if I draw oxygen, I put a circle around it, and I have 1, 2, 3, 4, 5, and 6 electrons. And then for hydrogen, I have a cross. So I will put 1 electron, and then over here, I got 1 electron. And let's combine all of this, guys. In the end, we get something like this. So I got 1 circle. I have 1 circle here, 1 circle here. And then here I got hydrogen, oxygen, hydrogen. And these are the crosses of hydrogen that shares with oxygen. They make 1 bond each. And then we got 1, 2, 3, 4. So we got overall, if you count the number of electrons around oxygen, you would see that you have 8 electrons. In acidic environment, I have another hydrogen, but this time this hydrogen doesn't have any electron. It has a positive charge. We know that if element loses electron, it becomes positively charged, right? Because we have, if I lose electron, I become positively charged. And this is what happens. This hydrogen doesn't have an electron, so it has a positive charge. So the oxygen in the water donates these 2 electrons to hydrogen. So water is electron electron donator, and this is electron, hydrogen is electron acceptor. So they make a bond, and it looks like this. So in this case, I'm gonna draw the shape. So I got oxygen, and I have here one bond, and one bond, and then I have here two electrons. Look at this, two electrons, and I have the hydrogen with cross dot, hydrogen, and overall this thing is a positive charge. So we put the positive on the outside, sorry. So it looks like this. And if you draw with the lines, the shape of it, it looks like this. The oxygen, so this and this, and we got two electrons, positive charge, but this bond will be shown as like this, because meaning that oxygen donated two electrons. So we have here, this is covalent bond, this two are covalent bonds, and this one is coordinate covalent bond. Okay, so I'm gonna show you the ammonium ion as well. So we start with NH3, and we know that it got 7 electron. Atomic number is 7, so 1s2, 2s2, 2p3. So we got 2 electrons here and 5 electrons here. And then hydrogen has 1 each, so 1s1. And then I start with nitrogen. I'm gonna put nitrogen here. I got 5 electrons, so 5. In this case, I'm just gonna combine them right from the beginning. So hydrogen has 1 each, so I'm gonna draw hydrogen. So hydrogen, I will bring in hydrogen right away. So with the cross, hydrogen, with the cross, hydrogen, with the cross. So if you count the number of electrons around nitrogen, you would see that it is 8. But in acidic environment, I said that I have another hydrogen, but this time hydrogen doesn't have any electron. So these 2 electrons in here will be donated to this guy, and we will make the new compound, and it will be looking like this. So I got hydrogen. This hydrogen is dot cross, this is dot cross, but this one is going to be 2 bonds, because this one here is coordinate covalent bond, while this guys, all these 3, they're all just covalent bonds. Okay, and if I draw the shape, this will be looking like this: nitrogen with hydrogen, and then I got here, this is another hydrogen, but this time I'm gonna draw this guy like this with an arrow, showing that this is coordinate covalent bond. The other ones are just regular bonds. Okay, just like so. And then I'm gonna do carbon monoxide too. I'm gonna do it in the bottom. So I got carbon monoxide. I know that the carbon electron configuration is gonna be 1s2, 2s2, and then 2p2. And oxygen is gonna be 1s2, 2s2, 2p4. That's why I'll have 6 electrons on this and 4 electrons on the carbon. So if I do carbon, I will have a circle 1, 2, 3, 4, and then for oxygen I'm gonna put 1, 2, 3, 4, 5, and 6. Okay, so this time the way it happens is that they're gonna start sharing electrons, okay, with each other, and then I will draw a circle like this. So I'm gonna put like this is oxygen, this is carbon. Okay, so in this case, the way this happens, if you go inside, so carbon donates 2 electrons. Carbon donates 2 electrons, while oxygen donates 2 electrons. Okay, so this 4, they're gonna be used for covalent bonding, and then oxygen is left with 4 electrons, right? I mean, yes, 4 electrons. But this time we don't have carbon. Octet rule is not completed. Octet rule is not completed yet. Okay, so oxygen will donate 2 electrons here, and it will make a coordinate bond, and this will look like this. So carbon, oxygen. So it will be like this, and then you'll have 1, 2, and then this will be looking like this, and then oxygen will have 2 of his crosses. So this 2 will be coordinate covalent bond, and this will be just a covalent bond. So this is coordinate. Okay, so and when you draw with the lines, it looks like this. So 2 bonds, and then this bond is gonna be looking like this, the triple bond, and then carbon is gonna be looking like this, oxygen is like this. This is the coordinate covalent bond right here. Perfect. So now we're gonna go into the new topic, and this is about hybridization. So I showed you some of you this picture where if you look at the legs of this guy, it looks like a zebra. Okay, but if you look at the head, such a nice face, we have a donkey. So we know that it is a mixture, or the hybrid of donkey and zebra. You mix them up, you made a new hybrid. Okay, and this is the same thing that we have in chemistry. I have here s orbital, sorry for the spelling problem in here, s orbital, and then I have here p orbital. You remember I told you p orbital looks like a dumbbell. It's actually looking like this. It looks like a dumbbell, it's not exactly a dumbbell. And when you combine these two guys together, we get a new orbital. It's called a hybrid orbital. In this case, we have a new orbital called sp3 orbital. And the shape of this is shown like this. When I draw it on the paper, I draw it like this, but electron cloud is actually looking like this under the microscope. Okay, so now we're gonna continue with the definition. Hybridization is in chemistry is defined as the concept of mixing 2 atomic orbitals. You mix 2 atomic orbitals to give rise to a new type of hybridized orbital. We're going to cover in 10th grade sp3, sp2, and sp, hybridized orbital. These are a new hybridized orbitals. But before I go, I want to tell you that each sigma bond is made by using hybrid orbital. You need to know this. So sigma bonds. So before I go, so let's say we have a methane, right? I got here 4 bonds. We know that how many sigma bonds in here. If you count it, you will see sigma here, sigma, and sigma makes it 4 sigma bonds. But if you look at this guy, I told you that the first bond is always sigma, and any other bond after is gonna be pi. So I got here sigma, 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 sigma. This one is sigma, and this one is pi. So I got 5 sigma, and then 1 pi. 1 pi 1. Now let's go and get back to hybridization. So let's see what happens through in electronic configuration. This is unhybridized carbon. So carbon we have here, we have 6 proton number, which makes it 1s2, 2s2, and then 2p2. I didn't show the 1s orbital in here, but instead we start with the valence electron, which is 2s2, and then 2p2. As you see, I have 1, 2, 3 orbitals in 2p, and I got 1s orbital in 2s. So overall, I got 4 orbitals. And then I have how many electrons? I got here 1, 2, 3, 4 electrons, and this orbital is empty. Okay, so I combined 4 electrons with 4 orbitals, and I made a new set of orbital. It's called sp3. If you look at here, I got 1, 2, 3, 4 orbitals, and I have 1 electron in each. Okay, so this time, if you remember, I told you we make sigma bonds, right? So I'm gonna use each of this electron to make a sigma bond. So I can make, in this hybridization, I can make 4 sigma bonds. Okay, but the reason I called it sp3 is because, as you see, I got 1 s orbital, and I have here 1, 2, 3, and 3 p orbitals. So I got 3 of this and 1 of s. So 1s plus 3p, we made sp3, and that's why we called it name sp3. So I can make 4 sigma bonds, right? So now let's look at the carbon methane again. So in here I have 4 sigma bonds, right? So when I have 4 sigma bonds, that means that my hybridization on this guy is sp3, because I have 4 bonds. I can make 4 sigma bonds. Okay, but now I'm gonna show you another type of hybridization. Okay, so but before I go, I want you to picture this carbon in your mind. So I have this carbon in the middle. So I made a new hybridized orbital, right? It's called sp3, and I have 1, 2, 3, 4 of them. I start locating them like this. Okay, and then this is the last one. So I got, sorry for the drawing, but this is approximately, okay, so I will try to make it prettier. So this is 1, 2, 3, and 4 sp3 orbitals, and in each one I have 1 electron. Okay, and then I have, in CH4 I got hydrogen, right? So hydrogen comes in with another electron, and he brings in, and they make bonds. Okay, they make bond here. So we made sp3 bond with 1s bond. The reason is hydrogen had electron in the 1s, right? So he brought in his s orbital, and then we had sp3, 4 sp3 orbitals of carbon. Okay, so each hydrogen brought 1s, 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 and then we have sp3, 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 and then sp3. So sp3, 4 sp3 orbitals and 4s orbitals. They combined and they made sigma bonds. Okay, now we're gonna go and discuss about the hybridization of other kind. In this case, I combine 2s with 2p orbitals, but I only take this 3 orbitals. I just took these 3 orbitals because I combined here S, 1p and 2p, and then I made a new orbital and I made this name sp2, and I have how many of them? 3 of them. Okay, so I have 3 of them, and this time I didn't touch the 2p. Okay, so I can make how many sigma bonds? As you see, I can make 3 sigma bonds. Okay, and this one is going to be left for making a pi bond, and I will show you how. So let's say I have C2H4 molecule. Let's start drawing the diagram of this. So I got carbon with 4 electrons, and then I have hydrogen each got 1 electron. This is not Lewis dot cross, this is a Lewis dot diagram, and here I connect this with this with this, and I connect this with this with this, and this with this. I still have the octet rule is not completed because I got 1, 2, 3 bonds, 1, 2, 3 bonds, and 1 electron. So this, they come together and they make 1 more bond. So it looks like this, right? So if you look at this carbon, I have 1, 2, and 3 sigma bonds, right? 3 sigma bonds. When I had 3 sigma bonds, what is my hybridization? It is sp2. Okay, so this guy has sp2 hybridization, and same thing with this. If you look at this carbon, got 1 sigma, 2, and 3. So this is sp2 hybridization too. And this guy is for pi bonding. If you remember, we had, for example, pi bond were looking like this, right? So on a px, we had like this. Py, it looked like this is py, this is px. And then we had a pz2, and this was looking like this. This is pz. Okay, now we're gonna talk about this carbons. We're gonna throw the orbital shapes on it. So I got a carbon in here, and then the way that one of the hybrid orbitals is looking like this, and the other one is looking like this, and the other one is looking like this. So these are sp2 orbitals, and then I have the other carbon, which is here. I'm talking about this carbon. It has a shape, so hybrid orbital looking like this, and then I have another one coming up like this, and the other one is looking like this. So I got sp2, and sp2 orbitals. So if you look, I told you that we have 3 sigma bonds, right? So I made each sigma bond with sp2 orbitals, and then hydrogen comes in with this 1s orbital. So hydrogen is here, is coming in here, and then another hydrogen with 1s. So they share electron. Then I have another hydrogen, 1 more hydrogen. They come here together and they made this shape. I have 4 hydrogens with 1s, and then I have left, if you see, I got left 2p orbital, right? And then I told you that p orbitals were looking like this. Okay, so I'm gonna draw the p orbital in here. What I have, this is the p orbital, and this is the other p orbital, and because each has 1 electron in it, right, they share this 1 electron, and they made a bond from bottom and top. Okay, so this bond in the middle is gonna be a sigma bond, but the bond up top and down, so this one and this one, they're gonna be all together one pi bond. Okay, and when you look at the picture, it looks like this. You see the pi bond from the bottom and top. You see this molecule from which angle I'm looking. So look from this top angle into this molecule, and you will see from top and bottom I have a pi bond, while sp2 hybrid orbital is looking like this. Okay, looking like this. So as in this case, I have here sp2 orbital here, I got one sp2 orbital here, so I have overall 3 sp2 orbitals. And same thing with this carbon, I have one sp2 and one sp2 here. I'm gonna show you the green ones, the p orbitals. So this one p orbital and this is the other p orbital. They combined together and they made a pi bond, while all the sp2s, they combined and they made a sigma bond. So when you look at this molecule, for example, I'm gonna draw it here again. You know that this sigma bond is made by sp2 of carbon and then sp2 of another carbon. Okay, while this bond is made by sp2 and then 1s of hydrogen. Same thing with this one, and this is again sp2, and we have 1s orbitals combined together. But this one is made by 2p and the 2p, because this is a pi bond. Okay, so I want you to guys to really draw this shape on your notebook so you can see. And the hybridization of this guy is sp2, because we got 3 sigma bonds on it. Now I'm going to show you another hybridization, which is the last one. In this case, I combine here one 2s orbital with one 2p orbital, which is empty, and I don't touch the other ones. This is the carbon again, 1s2, 2s2, 2p2. So here I combine this and this, so I combined 1s and 1p, and I made a new orbital, sp2. But this time, sp, and this time I have only 2 orbitals. You see, so I can make 2 sigma bonds. And in here, as you can see, I got 2p, so I can make 2 pi bonds. So now I want you to look at this compound when I have it in here. So I got 2 sigma bonds, right? And then if you look at here, I got 2 pi bonds. So when you have a 2 sigma bonds, the hybridization is going to be sp. If you check out this carbon too, you will see that it has 2 sigma bonds on it, so the hybridization is sp. And the way the shape looks is going to be looking like this. So I got 1 carbon, and then over here the shape, I told you the hybridization shapes are like this, right? So this combines with the other one, and then I have another carbon, so the hybridization of this carbon, and then hybridization. So we got sp orbital, I'm talking about this compound, sp, and then I have, so this is sp as well, so they share 1 electron with each other, and then I bring hydrogen with 1s, hydrogen comes with 1s, and then I have 2 pi orbitals, so 2 p orbitals. You see here I got 2 of them, so I'm gonna draw each one of them. So I'm gonna go with the red one. So I want you to, so this is one of them, okay, and this is the other one. And then I'm gonna show you one more. In this case, I have a P looking like this. Okay, so I got two P's. On each one, I got one electron, and then I have another P with one electron and then one electron. And here I got they share one electron with each other. So as we see, this one is gonna be a sigma bond. This is sigma bond, this is sigma bond. But this one's up top, we made a pi bond. So you see this green one and the red one. So I'm gonna go with the red one first. So I'll make a pi bond. So I'm gonna make a pi bond. So this is one bond from top and bottom. This is one pi bond. And then I make one more pi bond. In this case, I connect this P with this P, the green ones. So overall, as you see, I have here, in here I have one sigma and I have two pi orbitals. And then look at here, this is sigma and this is a sigma bond. And this is how it looks like. In the exam, we're not going to ask you to draw this, but I wanted to explain you how it looks like. So overall, when you have on carbon, for example, in this case, when you have on carbon 4 sigma bonds, that means your hybridization is sp3. When you have 3 sigma bonds, that means your hybridization is sp2. And when you have 2 sigma bonds on a carbon, your hybridization is sp. Okay? And if you look at this, guys, the degree angles on them, this degree is going to be 180 degree between two SPs. Okay? And if you look at sp2, the degree between this guys, this is 1 and this is 1, it is 120 degrees. 120 times 3 adds up to 360. The other one is 180. Got one top and bottom, 180 times 2. So 180 degrees, and this the first one is going to be looking like this. I showed you the molecule, and over here the degree angles between them is 109.5 degrees. So I'm just going to make a table down here where you have if you got 4 sigma, your hybridization is sp3 and your degree is 109.5 when you have 4. When you have 3 sigma bonds, your hybridization is sp2 and it is 120 degrees. And when you have 2 sigma bonds, it is sp and your degree is 180 degrees. This is the table that you guys can take a note and use it in your exam. Okay, so now we're gonna just review. This is the same thing, but I just in this case I want to take a look at the carbon. So in this carbon I got 1 and 2 sigma bonds, so this makes this guy have a hybridization of sp. This is sp as well. Over here I got 1, 2, 3, 4 sigma bonds, so this guy is sp3, and this guy has 1, 2, 3 sigma bonds, makes it sp2, and this is sp2 as well. And the degree over here is gonna be on this guy is it 180 degrees, and on this one is 180 as well. And this guy, the degree between them is 109.5 because it is sp3, and this one is, because it is sp2, the degree is 120 degrees, and then 120 degrees here as well. Okay, so we have this, and overall the summary table is here. So when you have a sp hybridization, you have a linear shape. That's the name of the molecular shape. You see it's linear, it's like a line, and the degree between them is 180. So the degree is 180, and then when you have hybridization of sp2, your degree is 120, and the name is trigonal planar, and it is shown in here. Okay, and then you have sp3 hybridization. You see I got 4 hybrid orbitals. You have 2 hybrid orbitals, 3 hybrid orbitals, and 4 hybrid orbitals. That means same number of sigmas too. Okay, so the degree is 109.28, or it is, you can write 109.5, it doesn't matter. And then yes, over here this is how it looks like, and the example shapes are given in the bottom. They all have the hybridization as given. For example, in here, this ones I showed you, the methane, and this guys. And these are the example orbitals. I told you when we had one, for example, CH4, the carbon, the bond we made was hybrid orbital with s bonding. This was sp3, and this was 1s orbital. And then, for example, if you do chlorine carbon C chlor 4, if you do it, we know that not like hydrogen, in chlorine the last valence electrons are located on p orbital, so they make bonding with sp3 and then p orbital. And then we had it in the middle. For example, we had this double sigma bonds. We know that this is made by sp2 and sp2, as we talked about for the other one. And then if you remember, the chlorine has again the pi bonding. So for example, for hydrogen, when you make it, it is 1s with 1s, right, the bonding. And then for hydrogen it is p and p, but it is 1s2 2s2 2p6 3s2 on a 3p with 3p 3p with 3p. And then we have here this guy, the hydrogen we talked about, and then chlorine again, you see s and p bonding, because 1s with the hydrogen, and then we got the 2p of 3p of chlorine, and this is hydrogen bonding. Okay, so the pi bonding I showed you, it was combination of 2 pi orbitals. They were making bonds like this. As you see here, they have it on the picture. It's like a sandwich, you know, from the bottom and top they cover electron cloud from here and from here. Okay, so these are the shapes. This is the name of this guy, Westberg valence shell electron pair repulsion. You know why it's called like this? The pair repulsion means that pushing away each other. Push away. So if you look at this guy, we have 2 orbitals, right? They pushed away each other as much as possible. 2 electron clouds. So we got electrons in here and electrons here, right? Because electrons are negative and negative, they push each other. So in here they pushed each other and they made an angle 180, and they called this a linear. And then in this case they pushed each other again, this ones, and they made a shape called trigonal planar. And we have here tetrahedral, the one for CH4, when you have 4 sigma bonds, and this is sp3. So you need to remember, so sp3 is tetrahedral. When you have sp2, it's trigonal planar, and sp is linear. But for this guy, I'm gonna show you the bent angular and the trigonal pyramidal in the bottom. We haven't discussed this ones yet, so look at this, guys. This is actually, you see the 15th group, this is NH3, and this is water. Water, I'm gonna write it as like this, and I will show you how. You see this pair of electrons, and you see the one in up top. So if you remember, we have drawn the shape of nitrogen, right, NH3, which is looking like this, this, and this, and we had 2 electrons. Let's start all over again. So nitrogen is 1s2, 2s2, and 2p3. So last shell we got 5 electrons, so I'll put 1, 2, 3, 4, 5. And then I make it like this, and then I have hydrogen. Hydrogen comes in with 1 electron cross. Hydrogen comes with 1 electron cross, and then hydrogen comes with 1 electron cross. So as you see, the shape looks like this, right? And I have 2 electrons in here. These 2 electrons are pushing these guys down, okay? And the name of this guy is gonna be called trigonal pyramidal. Okay, when you have a shape like this with the 2 electrons up top, this is called trigonal pyramidal. And now I'm going to show you the water. So water, we have oxygen. It is 1s2, 2s2, 2p4, right? So we got 6 electrons in the last shell. So we write oxygen, and then we go 1, 2, 3, 4, 5, and 6. And then I bring two hydrogens with 1s, so hydrogen comes here across, hydrogen comes here across. So now it looks like this. So I got oxygen with 1 bond, and then 1 oxygen like this. These 2 electrons, they go up top. This is the way it looks like, and they push this angle even further, more than this, okay? More than this, and then it makes, the name of this guy is called bent or angular. You can call it bent, or you can call it angular. Okay, so compared to, for example, methane, if you see here, I got over here methane, I got 4 bonds, right? So this one is called tetrahedral. When I change this guy with 1 pair of electrons, you see in this case, this is called trigonal pyramidal. If I change 1 more with the electron clouds, and it makes a new guy, which is bent angular. So you guys take a note of this ones, and it will be useful for you. Also, if you remember, I told you that we will come back to the topic. So do you remember the CO2 molecule that we had? So CO2, and the shape of CO2 is going to be looking like this, right in here. I've got two sigma bonds. That's why my hybridization is going to be sp, and it is going to be linear, right? So oxygen is more electronegative, so it withdraws the electrons, and this guy withdraw electrons. Normally this looks like a polar compound, right? Polar compound, because we have a polar bond. This is a polar bond. But the reason we don't have a polar compound, because these 2 vectors, they cancel each other out, and in the end we have a net of 0. That's why this guy becomes non-polar altogether, okay? And that's it for the coordinate, and this is overall why we have a non-polar compound.